Hello everyone. So today we are going to discuss about a new technique which is called as NOMA, non-orthogonal multiple access. So far we have done orthogonal multiple access where we studied in detail about OFDM. Today we will start another technology, another multiple access technique which is called as NOMA. So before I start discussion on NOMA, let us understand what are 5G and IoT requirements and how these requirements will be met by NOMA. So as we know, uh, we started with 1G, which was Advanced Mobile Phone Services, AMS, and then we had 2G, then you have 3G, 2G was GSM, 3G was WCDMA and high-speed packet access, 4G was LTE, and currently we have 5G systems in place. And these 5G systems, they give you high spectral efficiency, which means you are able to transmit more bits per second in a given bandwidth. And it also offers low latency. The latency is of the order of few milliseconds, and it supports massive device connectivity of the order of 200,000 per kilometer square. And it gives you a high data rate or high throughput or a high achievable data rate, offers you ultra high reliability and promises excellent user fairness, and it supports various quality of service requirements of different users, and this 5G technology is energy efficient. And this 5G technology basically is around three main pillars. One is which is called as enhanced mobile broadband, that is EMBB, which promises about 20 gigabits per second at the user interface. And the second is ultra reliable low latency communication. The communication is reliable and low latency of the order of 1 millisecond. And third pillar is massive machine type communication, which is MMTC. It can connect as high as 200,000 devices per kilometer square. And this is ultra reliable low latency communication. So currently these systems are deployed in the network, and people have now started working on 6G and beyond. So these are some of the requirements of 5G and IoT: massive connectivity, ultra reliable low latency communication, and enhanced mobile communication system, enhanced mobile broadband communication. Now, there are various multiple access techniques, both in orthogonal space as well as non-orthogonal space. So this is orthogonal multiple access, OMA, OMA, orthogonal multiple access. Under this, you have FDMA, frequency division multiple access. Basically, 1G system was around this. Then TDMA, the 2G system was around this. And then CDMA, 3G system was around this technology. And then 4G uses OFDM or orthogonal frequency division multiple access. CDMA is code division multiple access. TDMA is time division multiple access. And similarly in NOMA, non-orthogonal, this is non-orthogonal multiple access. Again, there are various variants of NOMA. One is PD NOMA, which is called power domain. NOMA. And then you have code division NOMA. And then you have pattern division multiple access, pattern division multiple access. and then you have lattice partition multiple access, lattice partition multiple access. Then you have a BOMA, which is building block, sparse constellation based multiple access. And then you have SDMA, which is space division multiple access. This is space division multiple access. And under CD NOMA, that is code division NOMA, there are different variants, which is SCMA. SCMA is sparse code. This is sparse code multiple access. And this is low density CDMA. And this is low density OFDM. So in this lecture, we are going to discuss about NOMA scheme, and in particular, we will take an example of PD NOMA, that is power domain NOMA, and we will see how PD NOMA, power domain NOMA, can be applied to VLC environment or visible light communication environment. So this is a basic difference between OMA and NOMA. In OMA, you have resources or RBs, resource blocks, allocated to the users. And this is shown here in this diagram A, where frequency resource block is allocated to different users. And in NOMA, all the resource block are given to the user, and the users have different power levels, but they have all the resource blocks. So whether it is a weak user or a strong user, they make use of all the resources available. So that's the basic difference between orthogonal multiple access and non-orthogonal multiple access. So this is orthogonal, and all these resource blocks, they are orthogonal to each other. So these are some of the advantages of NOMA over OMA. As we know, spectral efficiency and throughput, they are better in NOMA, because in NOMA, users have all the resources, irrespective of whether it has a poor channel condition or a strong channel condition. Each user actually has all the resources available to them. So which basically increases the spectral efficiency and the throughput. And it also, in terms of user fairness and low latency and massive connectivity, NOMA performs better as compared to OMA, because for example, in OMA, there are weak users and strong users, and priority is given to strong users, and thereby delaying the access to the weak user, which actually results into unfairness, or fairness is low, and also the latency in the system increases, and it is not able to connect large number of devices, whereas some of these issues are taken care of in non-orthogonal multiple access. So it is fair, it has low latency, and it can cover large number of users. So it has better features in terms of fairness, latency, and connectivity as compared to OMA. So before we start discussion on NOMA, it is actually based on a fundamental technique, which is successive interference calculation, which is also called as SIC. So let me spend next 5-10 minutes on explaining what is this successive interference cancellation and then how it is used in NOMA. So let us take a simple example. If you have two users, they have data x1 and x2. So the received data will be y is equal to x1 plus x2 plus noise. So this is the noise term. So this is the received data, and x1 is the from user 1 and x2 from user 2. And suppose x1 is transmitting at power p1 and x2 is transmitting at power p2. Then if you follow the Shannon capacity theorem, the rate will be less than log 2 1 plus p1 over n naught. And R1 will be max when actually P2 is 0. So this will be max when P2 is equal to 0. Similarly, R2, the achievable rate is less than log 2 1 plus P2 over n naught, and it will be max when P1 is 0. Now let us see the sum rate, R1 plus R2. It will be less than log 2 1 plus P1 plus P2 divided by n naught, where these x1 and x2 are IIDs. So we'll assume that x1, this data, which is user 1 and user 2 data, are IIDs, that is independent and identically distributed. Independent and identically distributed. So now if I plot these rates, R1, this is say R2, it will follow this kind of this thing, and here you have this is R1 max when P2 is equal to 0, R1 max, and this is R2 max, this point. So this is for a normal scheme. Now let us see for, now you can get actually some rate which is as per the area defined under this curve. So now my next question is whether is it possible to get higher sum rate? Is it possible to get higher sum rate? So now let us apply NOMA technique and see whether we are able to get sum rate higher than what we have got using OMA technique. So in NOMA, what happens? The higher power is detected first. So R2 will be log 2 1 plus P2 over P1 plus n naught, because the contribution from the user 1 is treated as noise. So the signal having higher power is detected first, and rest of the signals they contribute to the noise. It is noise for them. So that is why I have written this 1 plus P2 power in the user 2 divided by P1, which is the noise part, and the N0 is the normal noise. So if I see this point, this will be R2 will be somewhere here. So this point will be somewhere here. because this is P2 divided by P1 plus N naught. Noise component is higher, so it will be less than R2 max. And similarly, if I see R1, now once I have detected the P2, then I subtract the user from that signal, and I am left with only signal of user 1. So R1 will be log to 1 plus P1 over N naught, because P2 has already been subtracted. That is the basic principle of successive interference calculation. You detect the highest power, and then after you are detected, you subtract from the rest of the signal, and then again this cycle goes on. So R1 is equal to log 1 plus P1 by P2. And similarly, on the other side, I can have R1 log 2 1 plus P1 P2 plus N naught, and R2 will be log 2 1 plus P2 over N naught. So in this case, the power P1 has higher power which has been detected. The P2 is the noise in the system, and once you have subtracted P1, you are left with this R2. So if I plot all these values here, then I get so this is R1 max, it is somewhere here, and this is somewhere here. So this is say C and D. This point is actually R2 is A, this will be A here, and this point is C, and similarly you have the D point. So this is R1 log 2, so D will be somewhere here. So this is D, and then you have R2 max will be somewhere here. So basically now you are able to get, you can have combination of R1, R2 which lies in a curve which is given by a larger area as compared to orthogonal multiple access. So which basically tells that if I see the sum rate for case of NOMA, there is a possibility of getting higher sum rate provided you have chosen the power of different users in some appropriate fashion. So the sum rate in case of NOMA is higher, and this is basically use of successive interference cancellation technique to get data demodulated or get extracted from the composite signal. Now, having understood SIC, successive interference cancellation, let us try to discuss a downlink NOMA scenario, and we will try to calculate the achievable rate in case of downlink as well as in the case of uplink. So let us start with downlink. So downlink is, you have users having different powers. So suppose this is user U capital L, this is a power of capital L, Lth user, and then you have somewhere in the middle, say U small l user, and then you have this is a U1 user, and there are many users in between. So this is the power allocated to different users. This is power, and these are transmitted and towards the base station, and these signals are superimposed. So this is S is the point. This is S is superposition. And then user with the highest power is detected first. So in this case, you detect the user 1, so you get data of the user 1. This is signal detected, and then so on and so forth, U2, U3. And for ULF user, you will perform a successive interference cancellation technique for U1 to UL minus 1. This is L minus 1. So this will give you ULF signal. And similarly, to get data from the U capital L, you have to do SIC from U1 to UL minus 1. So this is how you extract the data using successive interference cancellation technique. So this is a basic diagram of a downlink NOMA network. So where you have users having different powers, U1 is the highest power. You detect that user first, then subtract from the rest of the users, detect the second one, and so on and so forth, till you extract the data from the weakest signal, which is U capital L in this case. So normally the bad user, or the which has a poor channel condition, is given higher power, and a good user which has a good channel condition is given low power. So this is how the power allocation is done for different users. So now let us try to understand signal SNR analysis for NOMA signal. Calculation of signal to noise ratio for NOMA signals. So now at the superposition point, that S, where all the powers are combined, is given by I is equal to 1 to L, where L is number of users, and each user is given some power, which is defined by the power coefficient AI. AI is the power coefficient, and PS is the power, and XI is the data of the ith user. So the S is actually summation of root of AI into PS into XI. AI is power coefficient, PS is the power, and XI is the data on the ith user. And this power coefficient, when you sum over all the users, is equal to 1. And we assume that A1 is greater than A2 is greater than AL. Now, depending on the channel condition, you allocate power to different users. So in this case, the power coefficient is highest at A1. And if you see, the channel condition of A1 is very weak, whereas the H1 is the H1 square, the channel coefficient is smaller as compared to H2 or H3, H4, and HL is the highest channel coefficient, and whereas is given the lowest power AL. So again, I'm repeating, the users which are having bad channel conditions are given more power as compared to users which have good channel conditions. So this is basically depicted from these two equations. So the data on the LF user will be given by HL. HL is the coefficient of the LF user into S is the superposition signal plus noise in the LF user. So this is the data on the LF user. And if I put the value of S here, in this equation. So this becomes HL summation I is equal to 1 to L AI PS XI square root plus NL. Now let us do the SINR analysis. So SINR J to L, actually this is the instantaneous SINR of the Lth user to detect the jth user, and j is less than L and j is not equal to L. This can be written as AJ PS, coefficient of the jth user, PS, HL is the Lth user, given by, this is the noise term which is coming from rest of the components, where I is from J plus N to L remaining users into AI plus the noise, which is sigma square. So this is the interference term, this is the noise, this is the interference term. And this power is the instantaneous power of the Lth user to detect the jth user. So I can write this AJ, this gamma can be written as PS over sigma square. So this can be written as AJ gamma HL mod square divided by gamma HL square summation this AI plus 1. So I have used the identity gamma is equal to PS by sigma square, which is actually the SNR, signal to noise ratio. So SINR for the Lth user will be AL gamma HL square divided by gamma HL mod square summation I is equal to L plus 1 to L. This is again the interference term, and here it is 1 because I have replaced PS by gamma square as PS by sigma square as gamma. So SNR for the Lth user is given as follows. And if I see the SNR for the last user, the LF, capital Lth user, where there is no interference, then this term will be 0 for that particular capital Lth user. Then I am left with A capital L, this is for the capital Lth user, gamma H L gamma square, HL mod square. Now let us try to calculate the sum rate. The sum rate of the downlink for, this is for our Lth user, rate NOMA, this is D stands for downlink, is given by log 2 1 plus SINR L. Now if I take the sum rate, before I take the sum rate, so this is expanded here, log 2 1 plus, this we have calculated from our previous discussion, AL gamma mod HL square divided by interference term and plus 1. The sum rate for the downlink will be sum over all the users, that is log 2 1 plus SINR L, and this can be written into two terms. One is up to L minus 1 users, and this is for the Lth user. So I is equal to, L is equal to 1 to L minus 1, and you have the SNR value for this, I have replaced here, and this is for Lth user where there is no interference. So this particular term will be 0. So this is for the Lth, capital Lth user. So the sum rate of NOMA D is given by this expression. So again, writing this again here, this is the total sum rate. This is actually R NOMA sum, and I am doing for downlink. So this is this value. So now let us try to see what happens at high SNR, that is just to get some better insight what happens at high SNR when gamma is tending to infinity. So when gamma is tending to infinity, our NOMA D sum will be equal to, because gamma tending to infinity, this term will be high. So 1 by gamma tending to infinity will give you 0. So I am left with approximately log 2 1 plus AL divided by I is equal to L plus 1 to capital L AI, because this term will be 0, plus the second term will be, because 1 is small as compared to AL gamma HL square, and when you take log 2 AB, the log 2 A, that is AL, will be very, very small as compared to other term which has gamma. So I'll be left with log 2 gamma mod HL square. So this is for when gamma tending to infinity. So this expression, above expression, can be approximated in this fashion. And this basically, because again gamma is tending to high, so basically this term will dominate as compared to the first term. So we get a very good, approximate and clean result for our NOMA sum for the downlink, which is log 2 gamma mod HL square. So this is the rate for the downlink, sum rate. So now this we have got expression for sum rate for the downlink. Now let us try to understand the uplink and also calculate the sum rate for the uplink. Everything is happening. Okay. Now we will discuss about the uplink NOMA. So we have calculated the sum rate for the downlink NOMA. Now we will calculate the sum rate for the uplink NOMA. Now let us first understand the how uplink NOMA works. So you have data x1 of the user 1. This is a user 1. So on and so forth. You have xlth user. XL capital L is the data on the lth capital Lth user. This is UL. So these data are superimposed in this block, and this received data goes to base station, and this base station performs the SIC function. So this basically part of the base station, it does subcarrier successive interference cancellation for U1 to UL, and you detect U1 to UL, the data from all the users. So this is how it works in case of uplink NOMA. So the downlink and the uplink are actually reciprocal. In one case, the SIC is happening at the user interface. In this case, uplink, the SIC is happening at the base station level. And base station, for example, in uplink NOMA, base station transmits power allocation, how different powers are allocated, because we are discussing power domain NOMA here, allocation, coefficient to mobile users. So this is in brief the uplink NOMA. Now let us try to calculate the sum rate for the uplink NOMA. So this is the point R here. If you see the R, receipt signal is summation coming from different users, HI root AI into PXI plus noise. P is the power, AI is the power coefficient, P is the total power, which is scaled by power coefficient factor AI. So doing SINR analysis, the base station decodes the signals of users in an order according to the power coefficient of the users. So power coefficient is high, that data is detected first, then it is subtracted from rest of the signal, and this process continues till you get the data from the last user. So SINR for the LF user is given by AL gamma HL mod square. This is the interference term plus 1, and L is equal to not equal to 1, because in that case there will not be any interference. So this will be 0. So SINR for the one user will be A1 gamma H1 mod square. And if you see the sum rate analysis, do the sum rate for the uplink. This is uplink. A summation over all the users, log 2 1 plus SINR, the similar way as we had done for the downlink. So this will have two terms. This is for the one user, and this is for rest of the user from L is equal to 2 to capital L. So this is log 2 1 plus gamma L is equal to 1 AL HL whole square. Now let us try to understand how we have got this expression. So this expression from here, how we have got this. So that let us do for two users to understand this. So two users, then R sum NOMA U will be log 2 1 plus, this is for L is equal to 1. So there is only one user, then this will be A1 gamma H1 mod square. So if there are two users, then this will have two terms, that is log 2 1 plus A1 gamma H1 mod square plus log 2 1 plus, so I am taking from this equation A actually, for two users. So this will be 1 plus A2 gamma H2 mod square divided by gamma A1 H1 plus 1. So this can be written as, we can rewrite this as log 2 1 plus A1 gamma H1 whole square plus log 2, I am taking H1 whole square plus 1, and this will be gamma A1 H1 plus 1 plus A2 gamma where I have simplified this equation, and this is log 2a plus log 2b, which is nothing but log 2ab. So this will give me log 2, and then this will get cancelled here, and then you are left with gamma A1 H1 whole square plus A2 plus A2 gamma H2 whole square. This is A2. this is gamma. So if I extend the logic for L is equal to 3 users, you will have one more term, which is A3 gamma mod S3 mod square, so on and so forth. So basically, if you want to solve this, then you will get summation of gamma will come out, summation of AL HL mod square. So this is how this has been solved. And now let us try to evaluate this expression for at high SNR, which is gamma tending to infinity. So gamma tending to infinity will give me, because this will get neglected here because gamma is very high. So I am left with approximately log 2 gamma summation over summation HL mod square from L is equal to 1 to capital L. So this is the expression for R NOMA sum rate for uplink. Now let us start comparing NOMA and OMA. So for OMA, that is orthogonal multiple access. The rate is given by alpha L log 2 1 plus beta L gamma mod HL square divided by alpha L, where beta L and alpha L are power coefficient. Beta L is actually power coefficient, and alpha L is the parameter related to specific resource of UL, nth user. So beta L is the power coefficient and alpha L is the parameter that is related to specific resource of UL. It could be frequency, for example. So RL OMA is given by alpha L log 2 1 plus beta L gamma mod HL square divided by alpha L. So R OMA sum rate will be sum over all the users, and the same expression here. And in OMA, it is this beta L and alpha L are actually equally divided among all the users, which is 1 by L. So putting alpha L is equal to beta L is equal to 1 by L. Then we are left with R sum rate OMA, which is summation 1 by L log 2 1 plus gamma HL square, because beta L and alpha L will get cancelled. So I am left with R. This is sum rate for OMA. So evaluating this expression when gamma is tending to infinity, that is at high SNR condition, this OMA sum rate will be given by 1 by L log 2 1 plus gamma HL square. Now the channel coefficient is in this order. H1 square is less than H2 and so on and so forth. HL capital H capital L mod square is the highest channel coefficient. So using this, we can write R OMA sum is equal to 1 by L log 2 gamma HL square will be less than, because I have replaced this HL by this H capital L, which is actually the highest. So this inequality is valid. So I can write this R OMA sum as less than or equal to this quantity. And this will be less than equal to 1 by L from the previous equation. And if I do summation, so it will be L times the same thing plus this L times. So L into 1 by L log 2 gamma HL square. So L will get cancelled, and this is the expression I get, which is R sum OMA log 2 gamma HL square. And if you see here, this expression is nothing but same expression as R NOMA sum downlink. So we can always say, because this less than is coming here, this less than or equal to, so therefore we can say that R, that is a rate, sum rate of OMA for downlink is less than or equal to R NOMA downlink sum rate for NOMA downlink. So the sum rate is higher in case of NOMA. Now let us see this example, a small example with two users. So let us understand this example with two users. So R sum NOMA, let us take for example the uplink, is given by log 2. This we have derived in the earlier slides. So this will be gamma L is equal to 1, capital L users, H L whole square. And so this will be equal to, for two users, log 2 gamma H1 plus gamma H2. This is for two users. Whereas if you see the R sum rate OMA for two users for under gamma tending to infinity, high SNR condition, is L is equal to 1 into L, 1 by L, log 2 gamma HL mod square. And this L is actually for OMA is half because there are two users. So L will be 1 by 2. So this will give me, half log 2 gamma H1 whole square plus 1 by 2 log 2 gamma H2 whole square. And we know this H1 square is less than H2 square. So if this is valid, then I can write this as, it will be definitely less than log 2 gamma H2 whole square. Now seeing this equation and this equation A and B, that is compare A and B, we can easily see that R sum rate OMA, this is an example of a two users, is less than R sum rate NOMA. So if you plot SNR versus sum rate, this will be some sort of, this curve will be for NOMA and this will be for OMA. So sum rate in case of NOMA, power domain NOMA, we have seen for both uplink and downlink, it is higher as compared to OMA. So this basically gives a basic feel about the NOMA, and then we will also see how this NOMA can be used in VLC environment. And later on also we will see, because the NOMA has been used along with MIMO, so we'll also see how NOMA and MIMO combination can be used in visible light communication systems. So just to briefly compare this OMA scheme and NOMA scheme and OMA scheme. So this is NOMA, the R1 rate user 1, this is for two users, this is log to the base 2 everywhere, is given by 1 plus P1 H1 square, P2 H1 mod square plus and naught, because this is interference and this is a signal of the user 1. So this is bits per second per hertz. And for R2, because you have subtracted the user 1 signal, you are left only with user 2 signals. So the R2 is given by log 2 1 plus P2 H2 mod square divided by N naught bits per second. So this is for NOMA. Whereas for OMA, alpha is the power, alpha are here the power coefficient, the parameter, the resource block, and which is given as R1 into alpha log 2 1 plus P1 plus H1 mod square divided by alpha N naught. And for R2, the resource block will be 1 minus alpha. So this 1 minus alpha will come here. So this is the R1 and R2 for OMA scheme. So this is in brief for two users, the rates of different users. And as we have seen in earlier discussion, that the sum rate, if you have chosen the power of the signals in such a way, you may get sum rate higher as compared to sum rate of NOMA higher as compared to sum rate of OMA. There are some issues with the NOMA. Let us discuss those issues as well. So it is actually the hardware complexity is very high because you have to do the SIC implementation either at the base station level or at the user level. So the hardware complexity becomes a little higher when you have more number of users. So basically you have to do the successive information, L times, because if there are L users. So this sometimes results into a delay. So there are techniques for to get rid of this complexity. In such cases, you make some clusters of users so that you are doing SIC only for limited number of users. So there are techniques to improve the delay part and reduce the hardware complexity part. Error propagation in SIC implementation. So basically, what we are doing, we are first estimating the channel. So the channel estimation becomes very crucial. So sometimes there is, center frequency offset or timing offset or some hardware impairments. You may not be able to estimate the channel coefficient highly accurately. So it might result into wrong decoding of the signal, which you are actually subtracting, so that error continues. So one has to be really careful in estimating the channel so that the error does not propagate in SIC implementation. And the third thing is you have to have optimal pilot allocation. For this, to get some perfect or near perfect channel state information, you have to allocate some pilot. So that design of pilot, how many symbols are needed, how frequently they are needed. So those are some of the areas which one has to work on. And then carrier frequency offset and timing offset estimation. In case of orthogonal multiple access, for example in RF, carriers frequency offset, that is CFO, and timing offset, they are estimated fairly accurately because you can distinguish the signals at the receiver end. So this correction can be easily done in case of OMA signals, whereas since the NOMA signals are overlapped signals, so this CFO estimation and timing offset estimation becomes a real challenging task. So these are some of the issues, and the research community is working to handle such issues, and we will find a good use of NOMA as we have seen in RF, in VLC as well. So my next discussion will be use of NOMA in VLC environment. So we'll try to understand why NOMA is useful or advantageous in NOMA and what kind of benefit we can get using NOMA. Thank you very much.